Okay, thanks for the introduction, and I hope you enjoyed the lunch break and have some fresh energy for this talk. In the next 15 minutes, it will be about a very important topic when it comes to software testing, but unfortunately, it's very often forgotten and ignored. And so it happened in yesterday's opening talk. I'm sure JB had actually a slide. He's just skipped it, where he wrote testing audio software. So this is what we are talking about today. And just to know who our audience is, maybe can you give a quick show of hands if you consider yourself a tester? Okay, fair enough. And whoever wrote a test, like an automated? Okay, that's much more. That's great to see. So before we get into testing, a few words about us. So my name is Christof, this is Nico. We are working for Adobe. For me, it's I'm with Adobe for 5 years. For Nico, it's 7 years, I think. And Adobe is a really large company. I have like 15 or 16,000 colleagues. I don't know everyone in person. And we have offices all over the world, and one of them is located in Hamburg, right at the riverside, which is a very inspiring site. And this office is the home for the majority of Adobe's audio team, which you can see here on the screen. And it's not just in Hamburg, we also have some colleagues in the US and India that are depicted on the screen during one of our audio team video conferences. It's from last year around Christmas, so the time frame matches. It's a bit too early with the red hat. And the audio team is responsible for all audio-related topics in the digital video and audio applications we have. Those are Audition, Premiere Pro, Adobe Media Encoder, After Effects, and Character Animator. But it doesn't mean that we do all the coding on our own. In some cases, it also just means that we do consulting, do code reviews, this kind of stuff. Within our organization, we have a very good reputation for automatic testing, and that's why we are here today. We want to share this with you. And I'm happy that there are so many people in the audience. Let's first reiterate on some vocabulary. What is black box testing? What is white box testing? So black box testing means you use the software like an end user would do. So you really started, sit in front, maybe you set up some hardware like control surface or audio interfaces, and you do end-to-end testing of whole workflows. The people doing this kind of testing are usually former musicians, audio engineers, audio editors, trainers who switched over to doing QE for our company. And usually they don't have a lot of knowledge about the internals of the software they test, but just see it from a black box perspective. On the far other side of the spectrum, we have unit tests. Unit tests are usually written by the programmers themselves, and they have all the knowledge about the internals, or at least they should have all the knowledge about the internals of the software. And they just pick a specific part, like a small unit, example-wise algorithms or data structures, and test them in isolation by feeding some parameters and checking the output against a well-defined output. We at Adobe have two kind of gray box testing things in between. There's surely much more, but just want to point out two that we do. On the one side, this is automated UI scripting. So we basically do clicks on the UI like an end user would do, and we hit the keyboard, we simulate keystrokes, all this kind of stuff. But it's scripted, so we can write it once and run it everywhere and anywhere. And in here you see how we automate our spectral editor. One more thing is automated tests on a scripting level. All of our products have a rather extensive SDK, and we will give a demo of that in the end of this talk. And we can use this SDK to trigger certain functionalities. And often we have some hidden APIs that are just available for us QEs and developers. So we have even more knowledge and can trigger functionality that is maybe not exposed on the UI level at all. With these four items, I'd like to show you how these fit into our overall test setup and how we run it. As you probably know, everything starts with code, and code should live in a version control system. In our case, this is Perforce. You maybe have Git or Subversion. This is very similar. And we have an automation server, which is a Jenkins instance. You maybe have heard of that. And whenever I do change to code and submit it to Perforce, this Jenkins server notices that and starts building our products and running tests again. So these are all the three types I just mentioned: UI tests, scripting tests, and unit tests. And these tests run on different types of machine, different operating systems, different OS versions, different CPU architecture, different graphic cards, just to cover as many different hardware setups as possible so that we catch things that maybe just occur on a certain machine one of our 1,000 users has. And whenever a test fails, we can issue an email to the responsible developer who did this code submission. At the same time, we measure performance numbers and log them to Splunk, which is a big data monitoring and analysis tool. And we mainly use it to plot graphs of performance indicators like startup time, mixdown times, DSP processing times, and all this stuff. And we send them out by email so that you can see whether there's something getting better or getting worse from build to build. Beside all this automated stuff running for every check-in, we have also our release engineering department who think the code on a daily basis and provide official builds. These are the builds that will go out to our end users in the end, but on a daily basis, they are provided to our black box testers so that they can do their job. And over the last couple of years, we really learned a lot about how we get the most benefit of the system, and this is what we want to share with you today. There are 4 little stories I want to tell you, and the first story starts with Time Tuner. Time Tuner is a technology that our team developed like 2 or 3 years ago, and it's used to shorten or lengthen video by either minus 10% or lengthen it by up to 10% without the user noticing it. It's not a stretch, it's really an intelligent algorithm where we analyze the video, look for areas of low action, do the cuts there, and keep the audio in sync. And we have automated tests for that, and in the beginning they were really a bit too dumb. We just took an input video, run it through the output through the whole workflow, and compared the output video against the baseline by doing frame-by-frame comparisons and audio samples by audio sample comparisons. And one day I got this email which said with build 104 there's an error. And it was quite easy to notice that there's a difference because I heard some crackling, some click and pop noises when I played it back, but I really didn't know what is actually the root cause for this. And it took me a couple of hours to find out what really went wrong. And the whole process involves a lot of micro edits on the audio side, so tiny little crossfades. And on one of the 2 stereo channels which we process, we didn't have a crossfade anymore, but we had a hard cut, and that's where the click sound came from. And as soon as I knew that, it was really easy to find out what the actual root cause is and which submission to the code was relevant for that. So I would have saved a lot of time if my test could have told me that. And after we ran through this process once, we adjusted our test and introduced a checkpoint in between. So we started with the whole analysis up to the point where we knew where to cut and how long to cut, and validated this cut list. And from there on, we just used a well-defined cut list as an input and run the remaining part of the process to test the audio rendering and then do the frame-by-frame and audio sample by audio sample comparison. And if now the same mistake happens again, just one of the 2 tests will be failing, and I already know where to investigate. And of course, one of those checkpoints is not enough. you need more than one. But it's the right direction. So my recommendation to you, whenever you write a test, be very precise on what you want to test. Don't test the whole workflow as such, but think about checkpoints so that you can divide the problem and can fix the issue easily when it comes up. But it's still good to have one test that catches all, because otherwise you might miss one of those embarrassing bugs that the user will recognize immediately. Second lesson learned is about our audio effects. So all of our products together ship with something like 70 to 80 audio effects. That's quite a lot. All of them have different parameters and a lot of presets, and all this needs to be tested. And we have a test execution suite just for that. In the beginning, it ran for 14 hours. So whenever you did a change, you have to run it for 14 hours, and then you know, okay, you're good, or you did something wrong. And this really was no feasible solution at all. It was really frustrating. So we spent some time to investigate why it is like that. And first thing was, we noticed a lot of time just got lost during UI automation. So all the clicks on the user interface, selecting the right preset from the preset pop-up and stuff like that. So we simply got rid of that and used scripting calls instead, reduced by factor of 2. And then we noticed that still there's a lot of time spent during the whole mixdown process for stuff that is actually not the effects itself, but the surrounding overhead code. So we stopped doing a mixdown, but directly fed the input audio to the effect instance itself and retrieved it from the output of the effect and validated it. And at this point, we thought, okay, now it's getting hard to further reduce the execution time, so we started thinking about parallelization, split the work into chunks, and run it on different machines at the same time. And now we're down to 1 hour until you know whether your change is good or not. But you need to have more machines, and you need to have the money for them. If you don't have that, you can also prioritize it. So it means you can simply skip the execution of some tests. And there are different mechanisms for that. You can do it on a business risk analysis, so you manually categorize your tests, how often you want to execute which tests, and you can change it over time. That's what we do for 3 test suites, like the check-in test suite, daily and weekly test suite. But there are also ideas about an automatic categorization where you can just maybe execute those tests that fail often, more often, because the area that is under test seems to be fragile and gets broken often. Or even more sophisticated, it would be to do an automatic detection which code has changed, and then just schedule those tests for execution that test this code that has been changed. So take away from here, don't burn time, rather burn money if you have it, or just prioritize it. To make your test system accepted, especially in a large team with many QEs and many developers working on it, it must be super easy. So it's not good if it takes a lot of time to deal with the test system, and this starts with the setup of the test system. A few years ago, when one of the tests was failing, a developer got assigned a bug, and then there was a reference to our setup manual, which started with how you sync the test system to your disk, how you set up the right passes, how you configure the product. You need to set some debug flags for that, how to download 200 gigabytes of test files, and then how to run the test. And you probably can imagine the reaction of the developers. Nobody is interested in doing something like that. And easy setup is key for success here. So today, our test system is so tightly integrated with our product that if you build the product, you already have everything you need to test it. And there's just one command line call that does everything for you. It downloads the test files, not all 200 gigabytes, but just those test files that are needed for the specific test. And it sets up all the parsers. It sets up the product so that it's in the right state, and all the hidden APIs are available and this stuff. And then you can directly attach the debugger and go for it. And another important thing is to avoid false positives. By false positives, I mean a test that is failed as reported as failing, but actually there's no issue in the code. Maybe there's an issue with the surrounding, with the test system, something like that. And there are various reasons for that. And just to name a few, a turned off display can cause issues during UI automation. Update warnings or dialogues on Mac and Windows can cause issues because you click on the update dialog that is in front of your application instead of clicking on the actual control. And when we come to audio, noise can be a problem. So in our application, we apply noise to our audio buffers from time to time to avoid problems with the normal, so it's just really, really silent noise. And if we change the execution order of calls, then it can happen that noise is added slightly different. And if we have a numeric instability in one of our DSP processors, this can yield to a large difference in the output that will then be noticed by the test system and report an error, even though it sounds still the same, but it's measurable. So really make your system easy, spend time on avoiding all these issues, because it will pay off in the long run. And the last lesson we've learned is that quality really matters. So most people, or many people, think quality matters for my actual code, but not for my test system, and consider it to be throwaway code. But that's not true. All the tags, keywords, buzzwords you've heard about good software development should apply to your test system as well. Because when your software changes quickly, covering other use cases and workflows, your test system must be able to follow. One example for that is the Essential Sound system that we have in our products, which is basically one of our approaches to make audio editing easy for audio novices. So people who don't have a lot of knowledge about how to configure effects and which effect to choose and all this stuff. And it's meant to be a one-click or one-slider approach for a rather complex process. And under the hood, we modify many parameters at once, where we just drag one slider. And we also have some automatic analysis of audio data to come up with the right settings of this dynamics effect, for example. And this technology was first only available in Audition, but due to our customer requests, we moved it over to Premiere Pro so that it's available in both applications. And from the software architecture side, it's important that your code is as flexible and modular so that you can move it over easily. But for your test system, the same thing must be true as well, because we can now run the same test in a whole different application with a different test environment, and everything works great. So we reduce the effort or avoided writing new tests, but can reuse our test system in a whole different setup. To sum all these 4 lessons up, and be precise, don't burn time, rather burn money. Make it easy, and quality matters. These are the general insights we want to share with you about testing, and we will now turn to testing audio in particular.
Yeah, thank you. So about testing audio in particular. So these are all general guidelines that will basically apply to most kind of, or a lot of kind of software development. So I want to spend a few minutes about tips and tricks, things that we do internally to test audio, which might be a little different, as you all know, to other software. And when it comes to audio testing, one of the first things that come to mind is dropouts. So dropouts is usually something that you don't have in other software, and usually if somebody comes new to the team, isn't or hasn't been dealt with audio software before, and you tell them you can't allocate on the real-time thread, it's, why not? But it's still an issue. If you don't know what I'm talking about, I guess at least 90% of you will, but quick recap, usually if you are processing stuff in real time on the audio thread, your processing happens in chunks. And whenever a new audio callback comes in, your chunk starts, you have exactly the time it takes to play back, in this case, or in this example, 512 samples to process your audio. And once you're done processing, you can push it to the audio output. In the meantime, if this would be a single core processor, your main thread could run. But whenever your audio thread blocks and you exceed your time, this is all a little bit simplified, then you get a dropout. And it's audible, and your users will hate you for it. So the question becomes, how do we automatically figure out that we have those issues? Because for once, if you allocate on the real-time thread or do anything that locks your real-time thread, it will not cause a dropout right away. It's not something that is deterministic. It's something that might happen very rarely. So one thing that we do is let's quickly sum up what can cause lock allocations. Mutexes, system calls, stuff like busy waits. But what I wanted to say is, how do we test for this? And one thing that we do is we have two computers. One is constantly playing back audio with different buffer sizes and feeding it to another computer that is just recording. And we use a very simple, well-defined signal like several overlapping sine signals we have here. And this image might be a little bit misleading because usually we use a digital output and have the same sample rate on the playback computer and on the recording computer. And during playback, we just do an FFT and search for all kind of spectral anomalies. Because if you have a well-defined sine overlapping, usually your FFT is quite clear. If you find an anomaly, send an email to the developers that you have some kind of locking issue. Now, when we're at the point that we know that we have some kind of locking issues, there are several ways to track this down a little bit. And although this is about testing, I thought it doesn't hurt to show you what we use for tracking down. And one thing that we use is this nice tool from Apple, which is called Instruments. That basically allows you to record events happening in your system threads and gives you all these nice indicators for reasons that one thread might have given up context or switched CPUs or whatever. You can get another display that shows you which thread ran on which CPU and when it switched CPUs, when your affinity fails. But there's one more thing that you can do with this little program that's a little bit less known. So Instruments builds up another tool which is called dtrace. And dtrace is a Unix and Apple inherent tool that allows you to write your own code, so-called probes. And with dtrace, you can write a probe that says, if somebody calls malloc or another function that you know it's not supposed to be called on the real-time thread, then lock your stack trace. This looks something like this. You can have a conditional. You can inspect thread IDs or thread names with dtrace. And the nice thing about this is, A, it interacts with instruments. So you can lock in instruments points in time where somebody called somebody or something on a thread where it isn't supposed to call something. And it doesn't require you to instrument your code. So you can do this on production code, which is quite nice if it runs on an automation system. That said, I still haven't found the time to write this probe that does malloc that does check for malloc on the real-time thread myself, so I haven't tried it. I'm pretty confident that it works. If somebody has tried, I would be curious to know about this. You have? Yeah. Okay, perfect. It works. So theory confirmed. Another thing that you can do, and I took this from Michael Tyson, who was mentioned a few times in this conference, is open source. If you are able to instrument your code, and this is something you should only do in your developer builds, you can write code like this that basically replaces a call to function like malloc that you don't want to call in the real-time thread. And in this case, just retrieves the function pointer using DLSim and does a quick conditional check if you're on the real-time thread by comparing against the thread ID or thread name. This is of course code that runs on Mac. You could write something similar on Windows as well. It's nothing that you should call on a production build because it will add an additional performance overhead, but it's something nice to have on your developer builds, and not just debug builds, but also release builds to just get some logs if you're doing something that might hurt. So much for logs. Another thing is unit testing with DSP code. I've been to this conference last year, and I've been to a talk about unit testing, DSP code. And one thing that was said during this talk stood out to me, which was basically it's very hard to test DSP code, and nearly nobody does unit testing on DSP code. And I typed into Google, why is nobody doing unit testing on DSP code? And this came up as an answer. The fact behind the problem is that the output of signal processing is hard to be fully and qualitatively defined, so inject input, run program, verify output approach does not apply well to signal processing. No. In fact, I would say the opposite is true. So if you have a DSP unit, and I'm not talking about your full plug-in processor, but a unit, a small thing like an FFT, like a filter, then usually I would say if you have a well-defined input, you should have a well-defined output. And if you don't have this, why? So DSP should be math. And to give you one example, what we did when we developed or rewrote our FFT library is we said, well, let's take this one step further and try TDD, test-driven development, with FFT, because FFT is very well defined from a mathematical standpoint. And we really started writing our tests before we wrote code. So we said, okay, if you feed in something empty, an empty signal, we expect a 0 output. If we feed in an impulse centered at 0, we expect a constant output. If we feed in a rectangular or a step function, there's a well-defined output. If we move the position of the step, the output should change accordingly. If we feed in a single frequency, we expect the according output. And if we change the phase of the frequency, the output should change. And the important thing is we wrote those tests before we wrote the FFT code. Because then if you write the FFT code and your tests are failing, you instantly know that you probably wrote something wrong. Or if it's a small deviation, you know you have probably to check for your numerical stability. Another thing why this is very important to have, especially in our code that runs on several platforms, several implementations, and we might want to use more specialized implementations. So like AAF framework, where we say they might be able to do faster FFT than we can for our custom code. Then we want to be able to run the same tests on all those implementations. We want to verify that AAF gives us the same results like IPP or whatever different implementation we might have. One of the final things we did is we wrote a test for IEEE 754. And you know what these numbers are, right? So at least if you've been to the quiz on the first day, you should know the first one is infinity, the second one is minus infinity, and the third one is not a number. So what happens if you feed not a number to an FFT? What happens if you feed infinity in there? The results should at least be the same on all platforms. This is what we do with unit testing. And in fact, at least for our core DSP library, we have a lot of unit tests that test this on a regular basis and that fail on a regular basis, which shows us it's good to have those tests. But as I said, this is for unit testing. And when I talk about unit testing, I mean small units, well-defined units. I wouldn't consider a plugin necessarily applicable for a unit test. If I see a full plugin with a full processor chain, I'm usually more thinking about integration or scripting tests like Christof just showed us. So what do we do on those kind of processors? We don't do unit tests on a complete plugin. What we do there is, as Christof showed in the scripting tests, we measure the plugin response every day and with every build. And if we know a plugin should never ever change output, it's a finalized plugin, we usually check for the MD5. So we want to know the checksum of the audio output should never change. This means if one bit in the audio output change, the checksum will change, and we know that there's some kind of issue. This, however, doesn't apply to all plugins. It doesn't apply to when you're developing a plugin and still working on the sound. Then your MD5 will change constantly, and it's pretty useless. So this is for final checking. Things you can do if this is not applicable to you is there are several measures of similarity of sound that we usually use in our code. And it depends very much on the use case which of those measures we use, and there are others that are also useful. One, and this applies for small occurrences of noise that you can't get rid of in our tests. Christof mentioned that we have this noise, but we can also remove it for testing, or we can fix it to a fixed seed that it's always the same noise. So we have some options to get rid of that. But if you can't, you can just say signal A minus signal B doesn't exceed a certain threshold. You can check for an identical or very similar spectrum. If you're not interested in the phase because you are not mixing the signal or whatever, you could just check for the spectrum. You can send, and this is one thing that I particularly like, a spectral comparison image whenever your spectrum changes, because it will instantly, you get an email, you see an image, and you see, okay, the high frequencies changed, the low frequencies changed, phases changed, amplitudes changed. This is quite a valuable tool. There are more out of the blues thinking kind of stuff, but I know that some companies, we internally don't use it, but I know some use cases for excitation function, which is basically a way to map whatever you're hearing to your inner cochlea to say, this is how your ear would react to a certain sound. If you have the same excitation function, something sounds very similar. And depending on how much this function changes, you know how much your sound changes. There are other features that I haven't used, never heard of being used, but things like MFCC could tell you in what way your sound changed. That's probably more of a development-like feature. There are others out there, and if you use other features for similarity measurements, then I would be interested to know about those too. Finally, while we are at plugin development stage, I always recommend measure as much as you can and measure it continuously. I know that plugin developers usually do measurements like impulse response of their plugins. When they develop, they do it once, they see it, they continue working, and a few days later they do it again. Do it on every build. If it doesn't change, you don't get a notification. If it changes, you will be interested about this, and you will make use of this history. You have a code history, why not have a test history? Amplitude statistics, spectral properties, THD, SNR, phase delay, all those things you can measure pretty easily and just pump out a history. And finally, if you're working on speech-related stuff, which I do a lot, things like an STI, so does my plugin negatively affect speech, is also interesting to know. And there are a lot of other papers out there with interesting methods that you can look up at this particular link, scholar@google.com. And that brings us to a small demo how we do testing with our script system, which might be interesting for you because you can use the same scripting system that we use internally. It's publicly available, so you can use it for plugin testing as well. With this, I give it back to Christof.
Okay, so just a quick demo how we test or partially test our plugins, those 70 to 80 plugins I've shown previously, and how we use our scripting for that. So maybe we start with the setup. So this is really something you can do on your own. If you have an Audition version installed on your machine, you need the latest version, which came out about 1 month ago. And you need a license for it, of course. And if you maybe stop it again. And up here, we document the setup. So as I already said, there are some debug flags we have that enable certain scripting APIs that are usually not public. So we have a public SDK, which is usable by everyone. We have a private SDK, which is just for our QE purposes. And we also have some beta stuff. And with the first call, debug set DBA scripting include namespaces effect API version 0.1, which is a pretty early version, and MD5, you can enable those APIs. And you just go to Audition, hit Command and F12 or Control and F12 on Windows to open the console, and then you can paste the first line to enable these scripting APIs, and you can paste the second line, which is to disable adding noise, which I described previously. So you don't want random noise coming up in your effect tests every time, because then you will get different results every time, and that's not what we want to test. So Nico already did this, and after that you need to restart Audition. That's all prepared on this machine, so we can directly start executing the test, and I will go through the code and explain it for you. So at the top we have the input path, the source file we want to open, and also the output name. So we will store the processed audio in a file. That means even if you don't want to use Audition for analysis, you can use this in a scripted way and compare the output file with another tool. So it's possible to use a special command line argument for Audition and feed in this script file, and then it will execute the script directly and shut down afterwards. And then you can just compare the audio with a different tool. And then we have here some variables which will say which effect we will apply, which preset we want to select, the parameter name that we want to change after selecting the preset, and the value that we will use for the parameter. And the amplify effect is an internal effect we ship with that, but you can also do the same thing with VST, VST3, and audio unit effects on Mac. So you can use it for your own plugin if you want to. So let's go to the first breakpoint, where we open. Okay, and do one step, please. And by doing this, we open the document in Audition. And yeah, so. And this is one of our favorite test files we use for effect testing, because it contains a lot of different stuff. There is dialogue in it, there is music in it, there are some dial tones in it, there is stuff with DC offset, there is an audio signal that goes above 0 decibel full scale. So we have a lot of edge cases, but also real-world use cases. And we are actually violating the first lesson learned, be precise. But if we want to be precise, then we need one small test file for every part of this file, and then we are running again in a problem with our execution time. So from the wave document, which was returned after opening the document, we directly get the effect rec, which is also visualized on the UI here on the left side. And from there we can access the first slot of this rec and insert an effect. We can either do this by the providing the effect name as a parameter, or also by providing the UID of the effect. And as soon as we do that, we will see it shows up in the effect rec on the left-hand side.
It should. There it is.
Yeah, okay. And so let's start with the basic stuff. We have capabilities to access all parameter infos, so all parameters that your effect provides. And we can enlist all the details, and maybe you just step forward until the next breakpoint so that we can see. So they are all done to the output here, and this is unfortunately pretty small. But if you go to the very top, you can see there is one parameter channel count, and link sliders, which is for UI. And here's the left parameter, so how much do we want to amplify the left channel, and it's the range from minimum to maximum, whether it's exposed to the user and automatable and all this stuff. So you can also do testing on this stuff, which is pretty basic stuff, but it might break. So it's probably worth to test everything. Then we can iterate over the presets that are exposed. And while doing this, we will check here. We will check here for the preset that has our predefined preset name, which was +1 decibel boost, and we will set this preset. And maybe you can now open the amplify effect on the user interface level. And unfortunately, we have an update bug in this part. So the preset was not configured here, but you can see everything is set to +1 decibel. So it was set, the preset. And now we can dump all the parameter infos by just getting the parameters by their name. And we can also set one parameter. Yeah, you see here, left is, it's not exactly one, but very close to one, and right is also set to +1 dB. And now we can set a parameter to a certain value. I think it was left to -3 or something like that. And in the end, we can apply the whole effect track. So it's also possible to assign other effects to the other slots, define all the settings you want to do, and then we apply it. And there's another update bug because the dialog for the amplify effect should actually be closed now. But you can see that the waveform has changed. And we need to wait until this process has been completed, which is usually quite fast. And we can now turn into the validation part, where we simply compute the MD5 hash of the wave document and can print this number out to the console or do verification based on that. And this is one thing we do if we know, due to refactoring maybe, the output of the effect should never change. It should really be exactly the same, bitwise the same. But in some cases, if you're doing normal developing and maybe adding a feature, you allow for small differences. And what we do then usually is to do a mixed paste approach where we invert the actual output and compare it then, add it to the expected output, and expect a 0 line or something that's close to 0 to come out. And unfortunately, this part is not publicly or available yet, and it's not under beta yet. But so if there's interesting in having more functionality available for scripting, we do this on a user-driven basis. So people come to us, ask for certain functionality being exposed. So come to us, talk with us. This is what you can do right out of the box if you have the latest version, and we're happy to engage with you to talk about the future of that. And one more thing is that we can save that file also to disk, which is quite easy, and then as said, you can use any other tool to do more analysis on the output file. And with that said, I think we open for questions of the audience. First question.
So first of all, thank you for the talk. It was really interesting. My question would be, I mean, you said you have like about 70 effects that you need to test. And I assume every single one of these effects has like up to 10, 15 parameters. So if I take it seriously, I would have to like do all the permutations of different parameter combinations to test it. So my question would be, what is your approach to that? Like, how do you select the parameter settings that you test?
So we basically just test the different presets we offer, because this is kind of the business risk analysis. We assume many people are, especially in Premiere Pro, for example, are just using the predefined presets and don't do a lot of changes. And it's biggest bang we get for the buck.
Okay.
So testing all parameter combination is very expensive, and but it's possible. So with that, you can modify parameters as you want to and run it. So if you decide to use Audition
execution
for your
time,
testing, then the execution time will go up.
Yeah.
But you can also, if you have your own, if it's your own plugin that is under test and you have full control over the code, you maybe can, well, it won't reduce the execution time. So you can add checkpoints in between, and well, it does reduce the execution time. So you can add checkpoints in between, like if you compute a gain curve, for example. You can say, okay, for my tests, I just compute the gain curve and write it to a file on disk and verify it with another script you write on your own, but don't continue the processing after just computing the gain curve. So there are possibilities to do that, but of course you have kind of a combinatorial explosion, and you need to deal with it somehow by cutting something.
Okay. Yeah. And maybe to add to that, so one thing that is in fact done and that I like to do when I have something like this and I know I work on a particular parameter of a particular effect where I know there will be changes. Audition is not just a wave editor, it's also okay. It's also a multi-track editor where you can set keyframes. So what I like to do is just have a sine, for example, and then have keyframes that move through all states of this one parameter over the sine, render this out to at least make sure that I see the difference, and then again I can get a spectral image, see how it affects the sine in different states, and you see where things like distortions, raise, and what changes there. So that's something you can do as well.
So one example where we really do that is our 5.1 panner, where we had some bigger changes recently. And there are a lot of parameters on the stereo width and the angle and all this kind of stuff. And we really went through every parameter, wrote automation for that, and just have a predefined session where the automation is recorded. And then we do a bounce of every track where we have the different automations, compare the output against a baseline. And we have also one track where we automate all parameters at the same time. So first be specific and then catch it all.
All right, thanks.
Any other question? Kind of complementary to testing, but do you also do like a static code analysis, for example, to catch if someone use OS calls in the real-time thread?
Yes, so that's something different that you can also and should do on the build server. There is third-party software out there for that, like Code Coverity, that we partially use, but there's also like Xcode has static analysis built in, and if you haven't played with it, you can actually instrument your build to generate HTML output for things that the static analyzer finds. And you can put that HTML on your build server, and then you can use that. We have started to play with that. It's not something that's currently running daily on our build system, mostly because, well, I started with this 3 or 4 weeks ago, and I haven't found the time to really dive deeper into this. But I found it interesting that it generates HTML output. That's quite nice, and it uses mouse hovering to navigate through your static issues. So that's a nice thing.
We have 2 more minutes. So okay.
What kind of library you use if you do the end-to-end tests? I know the library, for example, Siculi, that goes from the click tests and can move the pointer directly to an element. Do you use something similar, or do you apply or provide an interface that does the test?
You're talking about the automated UI script. Mm-hmm. So we have our UI framework where all the buttons and pop-ups and all the stuff is defined, and UI automation is already integrated into that framework, so we can directly trigger that functionality.
Makes it more stable then.
So we don't need any screenshot comparisons to find the right control. We are quite robust if you change the label of a button or something like that.
So that's one thing. I worked with some of those UI testing frameworks that come from third parties in the past. And the big problem you always have, if you change your font, suddenly it fails. And you spend a lot of time fixing false positives. And that is exactly the reason why we internally don't use those, but have our own internal UI automation.
I think with that, okay, a quick cheeky question.
It's actually about your very, very first slide. And
Very
you had a
good.
really nice headline, because that bothers us also a lot. It's the
First slide.
be
You're
precise,
making
or-
it hard.
this
This one.
Then
This
it's but you had this with division by 0.
Division by 0.
Ah, no, this one. Probably.
Yeah,
No.
this one.
Here.
This
this
one, testing audio, yeah. How do you overcome this issue? Because I've seen a lot of different ideas about it, and it's quite tricky.
Yes. So that's.
So usually the code gets ugly by doing that, but if you really expect there can be a 0, we just add an additional check and do the error case and error handling in the other branch of the if.
So you check before the division and you don't have a
Yes,
0?
we check before the division.
Okay. So it's not part of your division function, for example?
No.
No, we don't have callbacks for every division that check for. No, we don't. But you're right, it happens a lot. We're quite lucky that most of the time the automated tests find it, but we have nothing that does static analysis of the code. Although I must say code coverity, and I got some reports from code coverity in the past where it says a division through 0 might happen here, and then I add a check. But that's all that we do.
Okay, thank you.
I think with this we can wrap it up. Thank you very much, Nico and Christof.